Okay. Division of polynomials. This is going to happen. We're not going to necessarily have to go through all these steps all the time, but I want to make sure you guys understand that you can do this. You can do division of polynomials. So if I have the value, because again, the whole reason we're doing this is we're trying to simplify equations down to make them more manageable in smaller chunks that we can use. Okay, so here is our problem. Now this is our dividend. And this is our divisor. When I first came back to teaching, I had to look those up to make sure I had them right. So I didn't try to teach you guys completely something bonkers and crazy. Now, the way we do division of polynomials, basically we're going to be doing long division by hand. Okay, we can plug these into calculators, solve for them, but we're going to do this by hand. So when we're doing this, we need to understand how to write these values. So we take our dividend, we bring it down, so 15x squared minus 11x minus 14. It's going to be divided by 3x plus 2. So now, once we have it in this format, it's a little bit easier, not a little bit, a lot of bit easier to actually work through this. So the first thing we do is we look at the largest terms of each of these guys. So we start with the 3x and the 15x squared. What do we have to multiply this value with to get that value, or as close to it as we can? 5x. Price is Right rules without going over. So we have 5x. So now what we do is we take this and we multiply it through, just like what we did with the step above, multiplying our polynomials. So we end up with a 15x squared plus 10x. The 5x and the 2. Because remember, we have to multiply the whole term. So now, now we're going to subtract. So we're left with this, and we're subtracting 10x. So we are left with negative 21x. Because remember, we're subtracting the whole thing. This becomes a negative. Yep. And then we bring the next term down. And then we look again. We have this term, and we have this term, negative 7. So then we take our negative 7 times 3x, it's negative 21x. Negative 7 times 2, negative 14. Then we subtract the whole thing, which makes those positive. So now we've turned this back into a simple polynomial times a polynomial value. So the idea behind this is now we can go through and save this. Now, what if we had something left over? Yes?
So how did 11x turn to 10x?
So what it did is we just multiplied, we're just looking at the biggest terms. So we're looking at just the 3x, just the 15x. What do I have to do to get this to equal that? Yeah. So we do our 5x. So then we multiply the 5x times our 3x, which gives us 15. Then the 5x times 2, which gives us 10x. Then we have to subtract that whole quantity. So the positive 10 becomes a negative 10. The 15 becomes a negative 15. And then we just add them like we would normally.
So is there a reason? Is there a reason why the 11x isn't dropping, or like?
Because we have a negative 10x below it as well. So we have negative 10 minus 10, or negative 11 minus 10 gives us a negative 21. And then the next step we look at, what can I do here? So when we're doing these problems, it's also important to make sure when you have these guys, you list them out. If you don't have an x value, leave a space. Put 0x in there if you have to, just as a placeholder. Because this way, this will help remind you, okay, this should actually be down here. Because now we're at the end of the problem, we can't go any farther. Kind of as a visual clue for when we're doing this. Same way we would do regular long division. So basically the rules that we have, so look at the largest term for both the divisor and the dividend, which is here and here. Okay? What do we need to multiply to get those largest terms to be equal or to get as close as we can without going over? We put that value up here in the quotient. We perform the multiplication of the new quotient value and the divisor to get this value, which then we subtract, and then we bring down any extra values, and then we look at it again. So if this one would have ended up, if this wasn't 14, let's say this was 8, we would have ended up with a negative 8 left over. Can we get a 3x to turn into an 8? No. So this would be, this would be over the 3x plus 2. This would be our remainder. And the reason why that becomes, do what?
Negative 8 over 3x plus 2?
Yeah, negative 8 over 3x plus 2. And the reason that would become important is because we may have something down the line that where we have a 3x plus 2 multiplied or negative 8 somewhere, things are going to start canceling out. Generally, when we're doing electronics problems, that's why we're doing this stuff, is so we can get those get terms to fall out to make it simpler to solve. So then when we look at this guy again, instead of having to look at this value, we can now look at it so then if we come by somewhere, if we have a 5x minus 7 in our denominator somewhere, we can get those guys to cancel out. Make sense for now? Let's do another one. So we have 4x squared plus 2x minus 12 divided by x plus 2. So first thing we need to do, write this in our long division format. So the first thing I need to look at is the largest of these two terms. So I have an x and a 4x squared. What do I need to multiply the x to get it to equal 4x squared? 4x. So we plug that up in there in our quotient. We multiply the quotient by this. So we get 4x squared plus 8x. Then we're going to subtract this value from it. Those will fall away and cancel. And this we end up with a negative 6x. Then the next step we look at, can this go into this completely? We need negative 6. So we get a negative 6x plus 12. Yeah, negative 12. My apologies. Then we're going to subtract this whole value This becomes positive, this becomes positive. And this should have dropped down too. So the final answer is 4x minus 6 multiplied by x plus 2 is the same as this. Like I said, multiplication is usually easier to deal with than division. So that's all we're doing here is we're converting a division into a multiplication problem. Do you have a question?
What's another way to do it? I think it's called synthetic. But
Synthetic division? Yeah, there's that method too.
that only works on like pretty long. Synthetic is
Yeah.
I like those synthetics.
Okay. Let's do another one. I'm not gonna lie, those comments bring joy to my soul. That's your guess? Okay, well, let's divide it. Okay, so same steps. We look at the first term on each of these. What do we have to multiply an x by to get an x squared? Another x. So in this one, we actually don't have a space for it, which we should have. Yep, so x times x gives us x squared minus x, y. And then we subtract. So that's going to become a positive. Those go away. The biggest problem you're going to run into when you do these is you only apply the negative to this first term. You have to carry it, you have to distribute it all the way through the entire term. If you don't, that's when you're going to run into problems. So it's a -1 times that whole value. Okay, so now we look at this next step. We have an x and we have xy. What do we need to get this x to become a 4xy? We have to bring this other term down. Before I forget that step. So we need plus 4y. So then we multiply this across. So 4y times x is 4xy minus 4y squared. And we're going to subtract the whole thing. These are going to fall away. This is going to change into a plus. And we end up with, okay, now, can we get the x into the y? No, so that's as far as we can go. So this becomes our remainder. So we have x minus y times x plus 4y, and our remainder is negative 5y squared over x minus y. A lot of times when we're doing problems like this, these guys are going to end up falling away, and that's all we're going to have left. That's it. And those are going to be about as complicated as you guys will have on your quizzes. And there's not going to be a whole lot of those. But basically, just remember, just do the same steps. We didn't do anything different here than we did on the other ones. We just set it up to have our, just so I get the names right. Oops, good hell. We had our dividend inside the division sign, the quadratic, not the quadratic, the quotient. We have our divisor, and then this becomes our quotient up here. What do I need to have this value equal this value? Multiply the whole thing by that, subtract the whole value, bring anything down that we have, then look at the next step. What do I need here and here to get to match? Multiply the whole thing together, and then you'll have your remainder. If we had more terms, then we keep bringing them down. But this is one where I was telling you that this is where we need to insert. We need to have an x squared plus 0x plus 3xy plus 0y plus 9y squared, just as placeholders. So we can go through and look, if when I'm writing my answer, does this make sense as far as what values do I have, what values are coming there? Because there could be sometimes you'll see both of these guys ended up ones that weren't even in our original problem. And that might throw you for a loop when you're like, wait a minute, these didn't show up anywhere. But they are there, they're just zeroed out. Questions about that? Obviously, I know I'll get some more tomorrow when you guys run through the quizzes. Okay. Next stage we're going to look at is factoring polynomials. So if I have this value, 24a squared b squared minus 28ab plus 36ab squared. I want to write this into a more condensed number, one that I can use to manipulate, split things up as needed. We get into adding and subtracting fractions, things like that. Okay? So I'm going to factor. What I'm going to do is I'm going to pull something out of this that I can pull out of every single part of the polynomial. So when I'm first looking at this, what is something that I can pull out of this entire thing? An a. So we pull out an a. This becomes just a. This one goes away. That one goes away. We can't pull any more a's. Okay, what next? You can pull a b. That goes away. That goes away. That goes away. What next? A 4? You can pull a 4 out. So if we pull 4 out of 24, that's how much? Okay. So we'll pull 4. We're left with 6. We pull 4 out of 28. We're left with negative 7. We pull 4 out of 36. What was it? 9. Thought I heard it. 4ab. So is there anything else that we could pull out of there? No. So what we're left with is 4ab times 6ab minus 7 plus 9b. Now we've simplified it down into two, a polynomial and a monomial. But for one, we got rid of the squares. Do what? That's only when you're doing with square roots. Yeah. Okay, another example. We have 2a squared plus 8a plus 6. How can we factor that down? We take 2 out. Can we go any farther? Nope, that's it. So all we're doing, like I said, with all the reason that we're doing all these things is just to give you guys practice with the manipulation of values. Just because it's this value, a whole big long string, doesn't mean that's the end all be all of it. We can change it, we can manipulate it, we can get it to the point where a lot of times we'll have problems again where we'll have a 6ab minus 7 plus 9b that we are dividing it by. So now we can just simply cross those guys out when we're in a division problem. So that's the whole idea, is to get you guys thinking, how can I rearrange these polynomials into something that I can then get rid of? That's the whole idea, is we're trying to simplify it down based on what we're doing in electronics. Questions? Okay. Tomorrow we'll go over one more math. We're going to go over factoring trinomials. But I wanted to start getting into some series parallel analysis today. Let's get into some actual practical applications in electronics besides just this heavy math. Any questions about the math so far that we've covered? Like I said, we're reviewing it kind of fast, but this is the general idea of all the questions that we're going to be handling. Just, go through them systematically with what we've talked about. Make sure you follow the steps. They're just to get you guys thinking and going again. We good? For right now, at least? And if you do have questions, over the quizzes, please bring them. Bring them tomorrow. All right, so series parallel analysis. We need to solve circuits because a lot of times the circuits we're given that we're looking at, we're repairing, they're not just going to be simple series, not simple parallel. They're going to be some combination. So here is our opening circuit. We have R1, R2, R3. R1 is 160K. R2 is 240K. R3 is 120K. And our voltage is 7 volts. What I want to know, what is the current total? What's the voltage drop across R1? Voltage drop across R2? The voltage drop across R3? The current of R1, current of R2, and current of R3. So now when we're analyzing this, we have to apply the different rules depending on which part of the circuit we're looking at. So I'll give you guys a second kind of to copy that down. Yes. Yep, just slap it on there. So one of the first things that we're going to be doing is we want to basically reduce this down to a single equation. That's all we've been really doing, is reducing this whole thing down to a single voltage source, a single resistance source, and finding a single current source. And we can break these down step by step by step to do those. So in this case, I want to find my R total. The order of operations here is we want to do series first if possible, then we switch to parallel. So can you keep that in mind? Series is our primary for order of operations, if it can be done. So looking at this circuit, can we do anything with series? No, there's nothing available. So we switch to our next one, which we go to parallel. So now we have to look at our R total is going to be R1 plus R2 in parallel with R3. This is the notation I will use when I'm writing these guys. Series is going to be given by an addition sign. Parallel is our double slash. So now we need to solve, how do we solve for the parallel? Yeah, so this I'm going to label as R parallel total. Okay? R parallel total is equal to, there's two ways to do this one because again, we have two branches. We also can use the one that we can use every time, our reciprocal method. Product over sum. 80K. And how did you get that? Okay? So you can always use the reciprocal method. Always. One of the few options you can do is you can use the product over the sum because we have two branches. So now that we have this, the equivalent resistance of this guy turns into this. So one series resistor is our R parallel total. Those two combined together. Now we come back to R1. So we have 80K in series with 160K. So this becomes 240 kiloohms. Now that we have our resistance total, now we can go back through and we can calculate everything again. We can go through and we can solve for the currents. What are some of these that we can knock off the list just kind of so we don't have to do multiple steps? What are some of the other rules that we have? The what? So I had voltage first. Correct. Voltage of R2 is going to be equal to the voltage of R3 because those guys are in parallel. They're going to have the same voltage. Now the other one I heard who was talking about current. Okay? Right, which is, well, not just the value, but what is R2 and R3? What current is that? It's split up, so we have current coming through here. So we have total current. There you go. That's what I was looking for. So IR1 is equal to the current through R2 plus the current through R3. That's what I was looking for. I knew you were getting there. What's also the same current as what? Current total. Because R1 is in series with the power supply. There's only one current, so R1 has all the current. It's going to be the same current everywhere. So this is a good example of showing all of the rules at once. Okay? Current total is going to be the same in series. So R1 is going to have that same current total. R2 and R3 breaks up. It's going to split it up and then come back together. So I total is equal to IR1, which is equal to R2 plus IR3. So current splits, comes back together. Kirchhoff's voltage law, or current law, sorry. Hits this node, splits, goes through the resistors, comes back together, and then heads out. Okay? How to calculate it? Okay. So let's go with that. Let's solve for our I total first, and then we'll get to those branch currents. Okay? So our current total is equal to the voltage total divided by the resistance total. So we have 7 volts divided by 240 kiloohms. Yep. Okay, and micro is times what? 10 to the negative 6. So now we end up, we know we have 29.167 microamps. That's the current going through here, current coming down here. And we know that these two have to split up that main current. So now, to solve for the currents going through IR2, well, we can do it a couple ways. We can go through and solve for the voltages first, or we can go through and solve for the currents and then use the currents to solve the voltages. Either way. Okay? So let's look. So we have our current total. Let's look at the voltage drops. How do we get the voltage drop across R1? Current and the resistance. We can also use voltage divider as well. So we could have solved this before we found the current. So IR1, so the current through R1 is the same as the current total. So we have 29.167 microamps multiplied by the resistance, 160 kiloohms. Yep. So now if we have 4.667 volts being dropped across R1, how much has to be dropping across this network, our parallel total? Yeah, 7 minus the 4.667. Sorry, this is getting a little crowded. I will try to box set answers. Okay, so VR2 is equal to this. We know VR3 is going to be equal to that same value. So that's just another one we don't have to bother calculating. IR1, which we already found. Okay, so now we can go about finding the current either which way. So let's find these both directions, just so we can make sure our calculations are correct. So IR2, we have the voltage, we have the resistance, solve for the current. So the voltage across R2 divided by the resistance of R2, so we get 2.333 volts divided by 240 kiloohms. Okay, everybody good with that? IR3 is the voltage drop across R3 and the resistance of 3. So 2.333 volts divided by, come on, exactly, yep. And we use exactly a lot, but yeah, we have twice as much resistance as one as the other. So twice as much resistance is going to give us half as much current. Yeah. Yep. Because the inverse is how they all work. So the other way we could do it is we could also use current divider. So to use current divider, so remember we do the current through R2 is equal to the current total is the current total, or the current going into this branch, over the resistance total divided by R2. So again, we could put in the 29.167 microamps. We multiply that by the R total, which was 80K, over 240K. And when we plug that value in, what do we get? The 80K, that's the resistance total of that parallel network. Yep. So just what we calculated. I mean, within 10 nanoamps. Either way, it'll work. That's why we have these tools, is we can go throughout it whichever direction. Some people can prefer currents, some people prefer voltages. I prefer going through and solving for voltages where I can, and then deriving the currents later. But as a good double check, like I said, you want to make sure that these values add and subtract up to what they're supposed to be. So again, if we take these two values, add them together, what does that equal? 29.167. It better. Does that make sense as far as starting to where we're going to look through? Okay. We're going to wrap up here. I'm going to give you guys a homework problem to look at. Okay. So anytime we go through a circuit like this, all we have to do is go through and look at what is in series, what's in parallel. Get it down to a single resistance total. Combine your parallel branches, add them in series. If you have multiple branches or multiple resistors in a branch, add those together first. So your homework problem that we'll talk about tomorrow is I want you guys to analyze this circuit. Oh, wait. Scratch that one. So this is 2.2 k ohms. Hey, that's what you guys get to solve for me. Okay. Basically what I'm looking for basically solve for everything. Yes. Solve for your voltages, solve for your currents, solve for your powers. 2.0K. Yep, 2K. Do what? Yes. 125 ohms, 2.2K ohms, 2.2K ohms, 1.75K ohms, 3.5K ohms, 2.0, and 1.5K ohms. Yeah, 125 on the top. Yes. Yes. These two are in series, and I did that on purpose. Do what? Do your best. Like I said, I'm not expecting you guys to. I mean, I would love it for you guys to come in and answer this, but do your best tonight. If you can't get it, you can't get it. We will talk about this tomorrow. Yeah. So 2.2K, 2.2K, 2K, and 1.5K. Do what? Yes, both of them are 2.2. There is, and like I said, I want you guys to be like, oh crap, I don't know how to do this. This is way too much. Yes, I am a dungeon master. You had me at hello.